Hello, good afternoon. Hello, good afternoon. Dr. Shuku, Dr. Philip.
Yes,
Dr.
sir.
Shuku, Dr. Philip, good afternoon. Are you hearing me? Hello,
Yes,
Dr. Iloshuku, Dr. Philip. Dr. Philip
Yes, sir.
Ojo.
I'm hearing you, sir.
Okay, good afternoon. We are just two of you in the class. I think we can start because it's already 1 o'clock. Because the schedule is 1 o'clock is the scheduled time, so we can start. Can we start? Can I start? Hello, can we start?
Yes. Yes, sir.
Okay. So this afternoon, once again, good afternoon. So this afternoon, I'm going to be talking about ELISA briefly. Not going to take too long. ELISA is acronym for enzyme-linked immunosorbent assay. ELISA is an acronym for enzyme-linked immunosorbent assay. Are you hearing me? Are you hearing me, please? Hello, doctors, are you hearing me? ELISA is the acronym for enzyme-linked immunosorbent assay. Are you able to hear me? Can I continue?
I can hear you, sir.
Okay, thank you, doctor. So this technique was derived from the work of two authors, the work of McCartney and the work of Pierce in 1967. These two authors showed that antibodies could be labeled with enzymes for use in histochemical staining. Also, the work of Cat and Frigier in the same year, 1967, which was based on solid phase radioimmunoassay. So these are the works from which ELISA was derived. The technique itself was first described by Engvall and Perryman in 1971-72, and also by Van Wieman and Schulz in the same years. The technique is used for detection and measurement of large molecular weight proteins, such as viral, bacterial, and parasite antigens, and also for monitoring immune status.
I hear you, sir.
Okay, thank you.
Yes, bro. I hear you.
Okay, thank you, doctor. In enzyme immunoassays, antibodies or antigens are conjugated to enzymes in such a way that the immunological and enzymatic properties of each moiety is preserved. In enzyme immunoassays, antibodies or antigens are conjugated to enzymes in such a way that the biological properties of both the enzyme and the antibodies are preserved. Now, the degradation of a substrate by the enzyme, as measured spectrophotometrically, is proportional to the concentration of the unknown antibody or antigen in the sample. So this is the basis for this technique. Number one, that the antibody or antigen is conjugated to an enzyme. Number two, that this enzyme degrades a substrate, and the degree of degradation is proportional to the concentration of the antigen or antibody to which the enzyme was conjugated. So these are the basis for the test. The advantages of ELISA: it is convenient. The immunoreactants are stable for long periods. Thirdly, The use of chromogenic substrates for enzyme-labeled products permits visual interpretation of results. That is, the result can be visible to the naked eye because the substrates are chromogenic. Now, there are two types of ELISA techniques. We have the non-competitive and the competitive. So we have non-competitive and competitive ELISA techniques. In non-competitive techniques, number one, we have the direct ELISA. Of course, you know that ELISA involves the use of ELISA plates. So in this direct ELISA, the antigen is immobilized to a solid surface, which is the ELISA plate. So the antigen is immobilized to the ELISA plate. Thereafter, a primary antibody that has been labeled with an enzyme is added. So step number one, the antigen is immobilized to a solid surface. Step number two, an enzyme-labeled primary antibody is added to the plate. Step number three, the substrate is added. Now, when that substrate is added, the degradation of the substrate by the enzyme is proportional to the amount of antigen present in the sample. Direct ELISA, the sample, that is the antigen, is immobilized to a solid surface, that is to the ELISA plate. Step number two, an enzyme-labeled primary antibody is added to the sample. Step number three, the substrate is added. So once that substrate is added, the enzyme degrades the substrate. And then the degree of degradation of the substrate will be proportional to the amount of enzyme present, which is also proportional to the amount of antigen that was present in the sample in the first place. So that is the direct ELISA. Is very simple. Number two, the indirect ELISA. This indirect ELISA is used for antibody detection. The specific antigen is attached to a solid surface and is incubated. Step number two, the antiserum containing the antibodies is added. Then step number three, you watch off unreacted unattached products. The next step here is to add a secondary antibody, which is enzyme labeled. So the first step is to add the antigen. The antigen will bind to the plate. And then you add the antigen and then incubate the antigen bind to the plate. Second step is to add your antiserum. So once you add your antiserum, the antibodies in the serum that are specific to that antigen will attach to the antigen. Thereafter, you can wash the plate, wash off the unattached products. And then you need to add the secondary antibody, which is called the anti-immunoglobulin. Now, this secondary antibody is labeled conjugated to the enzyme. Now, once you add it, if for instance, your anti-serum, assuming for instance, the one that you added anti-serum from rat, for instance, your second antibody, which is conjugated, has to be an anti-rat, an anti-rat immunoglobulin. It has to be an immunoglobulin. It has to be an immunoglobulin that is accurate against rat IgG. So it has to be an anti-rat IgG that's conjugated to the enzyme. So step number one is to add your specific antigen, watch off unattached antigen, then you add your anti-serum, then there'll be antigen-antibody reaction, you watch off the unreacted products, and then you now add your secondary antibody, so that this secondary antibody is enzyme labeled, and then it's an antibody to the IgG that is in the anti-serum, so that this anti-IgG will attach to the IgG that was in the serum. And then thereafter, you can do the watching of the plate 3 times. And then you now add your substrate. Once you add your substrate, the enzyme that is conjugated to the secondary antibody will degrade the substrate. And then the amount of degradation will be proportional to the amount of anti-IgG, which is also proportional to the amount of IgG in the serum in the first place. So this is the technique that is described as the indirect ELISA. The third form of indirect ELISA is what is referred to as the double antibody or sandwich ELISA. Double antibody or sandwich ELISA. Double antibody or sandwich ELISA, which is useful for antigen detection. Step one is to attach the specific antibody to the solid phase. This is called the capture antibody in quote. So you attach the specific antibody, you coat the plate with the specific antibody. This is what is called the capture antibody. Step number 2, you add your test sample containing the antigen. You add your test sample which contains the antigen, which means the antigen in this test sample would be attracted to the specific antibody that had been adsorbed to the solid plate surface. And then you wash the plate. You incubate, and then you incubate for 30 minutes, and then you wash. The third step is now to add an enzyme labeled secondary antibody. An enzyme labeled secondary antibody. So this antibody is enzyme labeled. It's an antibody that's against the first antibody. It's an antibody that's against, that can get attached to that antigen. So get me well. Step number 1 is to absorb your specific antigen to the plate. Step number 2 is to add your sample which contains the antigen. So there'll be antigen-antibody reaction. Then thereafter, you wash the plate. The third step is now to add your enzyme labeled secondary antibody. Now this secondary antibody will attach itself to the antigen. And then remember that the antigen is already got itself attached to the antibody. So the antigen is sort of trapped within 2 antibodies. So that is why it is called double antibody sandwich ELISA. So after you have added that enzyme labeled secondary antibody and incubated, you now add the enzyme substrate and incubate. and then you stop the, of course, there will be degradation of the substrate by the enzyme. And the amount of degradation will be proportional to the amount of antigen in your sample. So this is the double antibody or sandwich ELISA. Those are the three types of non-competitive ELISAs. The competitive ELISA. This technique is useful in determining the concentration of a protein of interest in a sample containing a mixture of proteins. The technique is useful in determining the concentration of a protein of interest in a sample that contains a mixture of proteins. Your first step is to coat the plate with antibody that binds specifically to the antigen of interest. So you coat the plate with antibody that binds specifically to that antigen of interest. Step 1 is to coat the ELISA plate with antibody that binds specifically to the antigen of interest in the sample. Step number 1 is to coat the plate with antibody that binds specifically to antigen of interest in the sample. Remember, I told you that the technique is useful for detection of a particular protein in a sample that contains many proteins. So you have to coat your ELISA plate with an antibody that will bind to that specific protein you're looking for. Step number 2 is to block the plate with either bovine serum albumin or any detergent to prevent non-specific binding. Now, step number 3, you mix your sample. You get that your sample that contains the mixture of proteins. You get that your sample that contains the mixture of protein, and then you get another sample that contains only your antigen of interest, where that antigen of interest is conjugated to an enzyme. So step number 2 is to get that your sample which contains your mixture of proteins, including the protein of interest. So you get that your sample that contains that mixture, and then you have another sample that contains only that your antigen of interest, but is conjugated to an enzyme. And then you mix these two samples. So you get your sample that contains that mixture of proteins or mixture of antigens. And then you get another separate sample, which is prepared separately, containing only that antigen of interest, which is conjugated to an enzyme. You mix these two samples. The reason being that now you have two samples that you have mixed. You have a sample that contains your mixture of antigens. You have another sample that contains only your antigen that has been conjugated to that enzyme. So now the protein of interest in that your mixture of proteins is going to compete with the protein that is conjugated that have been conjugated to that enzyme. Both of these two proteins, you have two proteins. You have that enzyme in your mixture of protein, and then you have that enzyme that's from the other sample but has been bound to conjugated to the protein. So these two enzymes are going to compete to bind to the antibody that has been attached to the ELISA plate. That is why it is called competitive ELISA. So I said step number 1 is to coat your ELISA plate with an antibody that binds specifically to the protein of interest in your sample. Remember that your sample contains so many proteins, but your protein of interest is only one. So you have to get an antibody that will bind specifically to that your protein of interest So it is that antibody that you're going to use to coat your ELISA plate. That's step number 1. Step number 2 is to block non-specific binding sites in the plate. Step number 3 is to get your sample that contains your mixture of proteins, and then you get another sample that contains only the pure antigen but is conjugated to an enzyme. You mix these two samples, and the mixture is usually done outside. I mean, you mix the two samples before you add it to the plate, because if you say I'm going to add, if you say I'm going to add them separately, they are going to give one sample undue advantage over the other sample in the competition. So that is why you have to add your sample containing the mixture of antigens to the sample containing only the antigen that is conjugated to an enzyme. You have to mix them separately. You have to mix them together before you add them to the ELISA plate, so that you do not give any of the samples, any of the antigens undue advantage over the other. So after you have mixed them, you now use them to coat your ELISA plate, so that the competition for binding between the protein of interest in your sample and the protein that has been conjugated to the enzyme from the sample that was mixed together with your sample of interest, with your sample. So after mixing, add the sample to the ELISA coated plate. Now, the protein of interest in the sample will compete. The protein of interest in the sample will compete with the enzyme conjugated version of the same protein. That's what I'm trying to explain. The protein of interest in the sample will compete with the enzyme conjugated version of the same protein, both trying to bind to the limited antibody on the plate. The protein of interest in the sample will compete with the enzyme conjugated version of the same protein, both trying to bind to the limited antibody on the plate. So the next step after that incubation, you watch the plate, you watch away any unbound protein and enzyme conjugate. Then you add a colorless substrate, TMB, tetra-methylene benzidine. You add TMB substrate for a few minutes. The substrate will change to blue in color. After a few minutes, you stop the reaction by adding weeks of sulfuric acid. Now, the amount of color change is inversely proportional with the concentration of protein in the sample. The amount of color change will be inversely proportional to the concentration of protein of interest in the sample. If the protein of interest in the sample is much lower than the enzyme conjugate, majority of the protein of interest will bind to the antibody and vice versa. What that means is that if your sample contains low amount of protein of interest, it means that it is the conjugated protein that will bind more to the antibody. And then, if your sample contained a high amount of the protein of interest, it means therefore that most of the binding will be done by your protein of interest, and then less of the binding will be done by the enzyme conjugated version of the same protein. So that is why the amount of color change. Remember that the color change is determined by the enzyme, the color change is determined by the amount of enzyme. So that color change is determined by the amount of enzyme, which means that if the color changes much, it means that majority of the binding was done by the enzyme conjugated protein. It means that therefore that the amount of your protein in the sample was small. If the color change is less, it means that it means that the amount of binding was done by the protein of interest in the mixture of the sample, and then very little amount of enzyme conjugated version of the protein got attached to the antibody. That is why the enzyme the color change was small. Therefore, the amount of color change is inversely proportional to the concentration of protein of interest in the sample. Now, after this has been done, you can read the color change in a spectrophotometer, and then you can plot a graph of that color change. Of course, you run these samples with standards. Those standards have known absorbance and known concentration. Proteins with standard proteins that have known absorbance and known concentration. Therefore, after you have run the samples, you can plot a graph of your standards. If your standards are usually run either in duplicates or triplicates, so you find the averages, you find the means, and then you plot a graph. You find log of 1 over 1. You find the log of 1 over absorbance of the standard on the x-axis, and then you plot the protein concentration on the y-axis. So you have log 1 over absorbance on the x-axis, and then you have the protein concentration on the y-axis, and then you will draw a line of best fit across. Once that is done, and then if you know the concentration of your position of interest, you can extrapolate it from that graph, from that almost straight line graph. You can extrapolate your protein concentration from that graph. So this is the competitive ELISA. So okay, let me finish. Now the substrates for ELISA. For alkaline phosphatase, the substrate is p-nitrophenyl phosphatase. For the enzyme alkaline phosphatase, the substrate is p-nitrophenyl phosphatase, and it usually turns to a yellow color. So this enzyme will turn this substrate to yellow color. For the enzyme alkaline phosphatase, the substrate is p-nitrophenyl phosphatase. So this alkaline phosphatase will change that substrate to become a yellow in color. For the enzyme post-radish peroxidase, the substrate is O-phenylene-diamine. For horseradish peroxidase enzyme, the substrate to be used is O-phenylene-diamine. O-phenylene-diamine. So that's the substrate for the enzyme horseradish peroxidase. Also, for the substrate for the enzyme horseradish peroxidase, another substrate that is used is 3,3,5,5 tetramethylbenzidine. 3,3,5,5 tetramethylbenzidine. Let me repeat. For the substrate p-nitrophenyl phosphatase, The enzyme used is alkaline phosphatase, and we change that substrate to a yellow color. For the substrate horseradish peroxidase, for the enzyme horseradish peroxidase, the substrate is O-phenyldiamine. So that horseradish peroxidase will change this substrate O-phenyldiamine to a yellow color. For the substrate 3355 tetramethylbenzidine, the enzyme is also horseradish peroxidase. It changes this TMB to a blue color. Now, in this ELISA procedure, the watching of the plate is very, very important. It's an important step in the procedure. Now, the watching is to remove unbound or loosely bound reagents from the solid phase after each immunochemical reaction. It is necessary to wash the plate after each immunochemical reaction so that you can remove unbound or loosely bound reagents from the solid phase, which may interfere with your reading or which may give false reading. And also, the watching procedures are critical, and it is essential to ensure that all wells of the plates are treated the same way. So you watch the wells very, very well, and then once you watch, you actually take the plate and you hit the plate on a pad, on a tissue, so that you make sure that every drop of fluid is gotten rid of. Watching solutions. There are many watching solutions. The watching solutions include 0.9% sodium chloride. Watching solution that can be used, you can use 0.9% sodium chloride. Secondly, you can use 0.9% sodium chloride containing 1% human serum albumin. You can use 0.9% sodium chloride containing 1% human serum albumin. You can use 0.9% sodium chloride containing 0.5% twin 20. 0.5% sodium chloride containing 0.5% twin 20. Number 4, you can use 0.15 molar PBS. You can use 0.15 molar PBS, pH 7.2, containing 0.15% twin 20. 0.15 molar PBS, pH 7.2, containing 0.15% twin 20. Lastly, you can use PBS containing 0.05% twin 20. So the watching solutions, you can use 0.9% sodium chloride. You can use 0.9% sodium chloride containing 1% human serum albumin. You can use 0.9% sodium chloride containing 0.5% twin 20. You can use 0.15 molar PBS, pH 7.2, containing 0.15% twin 20. Lastly, you can use PBS containing 0.05% twin 20. Now, in doing ELISA, oftentimes you are going to do your own ELISA if you are not using pre-made kits, sometimes you need to make some solutions. To make some solutions, you need to be reminded about some basic definitions, because these definitions will be important for you to know when you want to make solutions. A one molar solution is a solution that contains 1 molecular weight of the solute in 1 liter of distilled water. A 1 molar solution, 1M solution, 1 molar solution is a solution that contains 1 molecular weight of the solute in 1 liter of distilled water. A 1 millimolar solution, 1 small m, capital M, a 1 millimolar solution is a solution that contains 1/100 of the molecular weight of that solute in 1 liter of distilled water. A 1 millimolar solution is a solution that contains 1/100 of the molecular weight of that solute in 1 liter of distilled water. A 10% weight for volume solution, a 10% weight for volume, that is W/V, a 10% bracket weight for volume, or a 10% bracket W/V, a 10% weight for volume solution is a solution that contains 10 grams of the solute in 100 ml of distilled water. A 10% weight for volume solution is a solution containing 10 grams of the solute in 100 ml of distilled water. A 10% volume for volume solution, or a 10% bracket V for V/V solution, is a solution that contains 10 ml of the stock solution weighed up to 100 ml with distilled water. A 1 molar solution is a solution that contains 1 molecular weight of the solute in 1 liter of distilled water. A 1 millimolar solution is a solution that contains 1/100 of the molecular weight of the solute in 1 liter of distilled water. A 10% weight for volume solution is a solution that contains 10 grams of the solute in 100 ml of distilled water. A 10% volume for volume solution is a solution that contains 10 ml of the stock solution made up to 100 ml with distilled water. Let's talk about dilutions, because in doing ELISA, you need to use dilution. When you say 1 to 1,000 dilution, 1 to 1,000 dilution, 1 to 1,000 dilution, it means you take 1 ml, of the serum or 1 ml of the solution, and then make it up to 1,000 ml in water. It means you take 1 ml of the solution, 1 ml of serum, or 1 ml of antigen if it's in liquid form. Then you make it to 1,000 ml. You take 1 ml to 1,000 ml, which means 1 ml is the same thing as 1,000 microliters. It means that you take 1 ml, which is 1,000 microliters, into 1 million microliters. That is into 1 liter. That's into 1 million microliters. Now, if you do your simple arithmetic, that would be 100 microliters into 100,000 microliters. That is also 10 microliters into 10,000 microliters. That is also 1 microliter 1 microliter into 1000 microliter. So that is the dilution. That's how to work out the dilution. Now, assuming that you want to coat 2 96 well ELISA plates, and you want to coat each well with 100 microliters of serum. So you have two 96 well ELISA plates. You want to coat these 2 wells with 1000 microliters of serum, and this serum is diluted at 1 to 100. You have 2 ELISA plates. You want to coat these 2 plates with serum diluted at 1 to 100. Now, how do you go about it? These 2 96 well plates, we need 2 times 96 times 100 microliters of serum. That is 2 times 96 times 100 microliters of diluted serum. That will give you 192. That will give you 19,200 microliters. So you have 2 plates, 96 well plate, and you want to coat each plate with 100 microliters. So these 2 plates are going to take 2 times 96 times 100 microliters. If you multiply it out, it's going to give you 19,200 microliters of diluted serum. So you are going to need 19,200 microliters of diluted serum. Now, for each 100 microliters of diluted serum, you need 1 microliter of the original serum. Now, when you are doing ELISA, now you have calculated you are going to need 19,200 microliters of diluted serum. You will not base your calculation on this 19,200. You actually have to get a volume that is higher, because when you are doing your pipetting, there may be little wastages along the way. So instead of wanting to prepare to use 19,200 microliters, you may want to use 20,000 microliters of diluted serum to make room for any possible wastages. Now, for each 100 microliter of diluted serum, you need 1 microliter of the original serum. Therefore, since you are going to need 20,000 microliters of diluted serum, if you do your simple proportion, you are going to need, that is to say, you are going to need 1 over 100 times 20,000 microliters of diluted serum. So 100 microliters of diluted serum, you need 1 microliter of the original serum. If you are going to need 20,000 microliters of diluted serum, the simple proportion is this: 1 over 100 times 20,000 microliters. That will give you 200 microliters of the original serum. So what that means is that you are going to prepare 200 microliters of your original serum, and then you make it up to you prepare 200 microliters of that diluted of your original serum, and then you now make it up to 20 mils or 20,000 microliters, which is 20 mils. So you get your 200 microliters of your serum, and then you add your diluent to make it up to 20 mils. So that will give you serum that have been diluted. That will give you 20 mils of serum diluted at 1 to 100. So from that, you can now conveniently coat your 2 ELISA plates with 100 microliter per well. Now, let's talk a little about how to dilute antigen. Well, I'm a hematologist, so I work with helminths. Most of the optimal antigen concentration usually varies, but usually ranges from 1 to 10 microliters per mil. Sorry, 1 to 10 microgram per mil. So, for instance, you get the fluke, get your fluke, or you get your homunculus, and then you have prepared your antigen, either somatic antigen or excretory secretory antigen, and you want to coat your ELISA plate. The concentration you are going to need you are going to dilute up to maybe anything between 1 to 10 microgram per mil. But normally you have to do what they call you have to titrate the antigen or the serum to know the optimal concentration. But if you range from 1 to 10 microgram per mil. Now still, assuming, for instance, that you have this your 296 well plate, I want to coat each plate with 1,000 microliters of antigen diluted at 1 microgram per mil. You have your 296 well plate. I want to coat your plate with antigen that have been diluted to 1 microgram per mil. And this original, you have diluted this antigen to become 1 microgram per mil from an original protein concentration of 4 milligram per mil. So the antigen you got from your crude extract, for instance, from the extract was 4 milligram per mil. But the antigen you want to work with for ELISA is 1 microgram per mil. So how do you go about it? Now, you have your 2 ELISA plates. And these are 2 ELISA plates. Each of them have, you want to coat each plate with 100 microliters. Therefore, we are going to need 2 times 96 times 100. That's approximately 20,000 microliters, as we said before. And then the dilution needed is 1 microgram per mil. 1 microgram per mil. That is, each meal should contain only 1 microgram of each meal that you take to contain 1 microgram. But you need 20,000 microgram. So each meal of your diluted antigen should contain 1 microgram. But you need 20,000 each microliter should contain 1 microgram. Each microliter should contain 1 microgram. But you are going to need 20,000 microliters. So each microliter is going to contain 1 microgram. So this 20,000 microliters is going to contain 1 over 1,000 times 20,000 microgram. That means it's going to contain 20 microgram. Each microliter should contain 1 microgram. But you want 20,000 microliters. So these 20,000 microliters should actually contain 20 microgram. Now, your stock antigen is 4 milligram per mil. 4 milligram per mil. 4 milligram per mil. Which means that this stock antigen is 4 milligram per mil. Which means it contains 4,000 microgram per 1,000 microliters. So it means that 1,000 microliters of this your antigen contains 4,000 microgram. 4,000 microgram is equal to 1,000 microliters. But you are needing only 20 micrograms. 4,000 microgram is equal to 1,000 microliters. But you need just 20 micrograms. Therefore, 20 microgram that you need will be 1,000 over 4,000 times 20. That will give you just 5 microliters. So what you need is just 5 microliter of that your stock solution. So what you need to do just to prepare it is to prepare just 5 microliters of that stock antigen and dilute, make it up to 20 mils or 20,000 microliters. That will give you the antigen dilution at 1 microgram per mil. And then you can now use that one to coat your ELISA plate at 1 microgram per microliters. Well, this is all about ELISA. I hope you have followed me. Let me try to, I don't know. Do you have any question or you want me to go through? You want me to go over the calculations or you want me to go over the procedures? Hello, are we together? Hello? Hello, are we together?
Yes, sir. Yes, sir.
Okay. You want me to go over which aspect do you want me to go over? Because I know it may be a bit confusing, especially the calculations. Do you want me to go over any aspect of this presentation?
Sir, a question, please, sir.
Yes.
Thank you for the wonderful presentation, sir, and the lectures. Sir,
Thank you.
in quoting the antigen,
Yes.
I can see 19,200 microliters, and the second one I can see 20,000. Can we approximate, sir?
Yes. What I'm coming. Let me go back to the slide. I've gone out of that place.
Okay, sir.
Yes. Let me go back to the serum. Now,
Okay,
each of these 96 well plates.
Yes, sir.
You are going to coat with 100 microliters. So for
Yes.
two plates, you are going to coat with 2 times 96 times 100. That will give you 19,200 microliters. You understand, Cole?
Yes, sir. Yes, sir.
Now, when you are doing the laser, you don't work with exact amount. You usually want to work with a figure that is higher than what you need, because
Okay, sir.
because when you are pipetting, you're going there's going to be some wastages. That
Yes,
is
sir.
why, for instance, in your serum, instead of trying to get 19,200 microliters of diluted serum,
Yes,
I opted to work with 20,000 microliters of diluted serum, so that when I go to the antigen aspect, that antigen will have actually needed the same amount of antigen, 19,200 microliters, but I just decided to take 20,000 microliters to make room for any possible wastages in the procedures.
Thank you very much, sir.
That is the reason. Yes, thank you.
Thank you very much.
Any more questions? You want me to go over the calculations again? Does anybody want me to go over the calculations? Is there any aspect of this presentation you want me to go over?
But I believe that when we read, so we can maybe jot down our questions, and if it's possible, you drop your number so we can communicate with you.
Okay, I will. Okay, can I give my number? Hello, are you
Yes,
here? Are
sir.
you with me? 0803
Yes, sir.
0803
Okay.
593
Yes, sir.
0440 0803 593 0440. But I believe
Okay,
that
sir. Thank you, sir.
if you take your time to go over them, they are not as difficult as they may appear. If you take your time to go over them, and then you can also Google the procedures, you understand them better. I think the only complex one seems to be the competitive ELISA. But if you go over it, I've tried to. If you Google competitive ELISA, some of them they will describe some complex procedures. But what I've done is try to simplify the procedure in such a way that you can understand it. But I think that's the only one that appears a bit not too straightforward. But the way I've put it, I've tried to make it as straightforward as it can be. If you Google it, there are some sites that will give you complex description that you may not be able to follow. But anyway, you can always get in touch with me by phone, through phone. So, are we together? You said did you say I should upload my presentations to you people?
Yes, sir.
Okay, I will try to do it. Okay, just hold on, give me some minutes. I'm coming. I'll get back to you. Just stay on, please.
Okay, sir.
Hello, I'm trying to upload the document, please. Just hold on. I'm trying to do the uploading. Just give me some minutes. We're in the process. Are we together? Give me some minutes. I'm in the process of uploading, please. Are we together?
Yes, sir.
Yes, sir. Yes, sir. Yes, sir.
Hello? Hello?
Yes, sir.
I think what I'm finding it difficult to upload. I think what I will do, I will send it to Dr. Chadu's email in a few days' time, and then he can share with the group.
Okay, thank you very much, sir.
Okay, thank you. Okay,
Okay, sir.
okay, thank you. So,
Thank you, sir.
can we close the meeting?
Yes, sir.
Okay, God bless you. I appreciate it. Thank you. God be with
Thank
you.
you, sir.
Same.
Yes,
Thank
sir.
you. So, you know what? Okay, that's good. Okay, that's very good. That's good. That's good. That's good. This is your number, cool? Okay, I will call you back. I'm in the class. I will call you back. Call you back. Thank you.
On that.
So I was still expecting the lecture notes.